Morning. Now, this is class 3 of our chapter Crystallography. Now, today we will learn about some simple crystal structures. So, this session is very important because this is most probably this will be asked as an essay question, that is, discuss the various crystal structures. Okay, so that is what we are going to discuss today. Only that portion, the various crystal structures. Okay, now crystal structures are broadly classified into two. One is close packed structures and the other is loose packed structures. Okay, now these close packed structures are again divided into two. They are hexagonal closed packed structures or HCP, and the other is face centered cubic or FCC. Okay, then the loose packed structures are again classified into two. They are body centered cubic BCC and simple cubic SC. Okay, so I will give you a brief introduction. So, crystal structures are broadly classified. Crystal structures are broadly classified into two. They are closed packed structures and loose packed structures. Now these closed packed structures are again classified into two, which are the hexagonal closed packed structures, that is HCP, and face centered cubic FCC. Now these loose packed structures are again classified into two. They are body centered cubic BCC and simple cubic SC. So this is the classification. Hope you understood. Now, first of all, we have to discuss what is closed pack structure, what is loose pack structure, then what is HCP, what is FCC. Each of them has got certain features that you have to write in points, and you have to include examples also. Then about BCC you have to write, about SC, and what are their specifications, I mean the various features, then a simple structure, as well as some examples. Okay, so let us start with the definition for closed pack structures. It is mainly seen in monatomic crystals having non-directional bonding such as metallic bonding. Here, one of the most important point regarding closed pack structure is that their coordination number. Coordination number means number of nearest neighbors. Okay, that is coordination number of each atom, that is each atom is surrounded by how many neighbors, that is what it is meant. Okay, so coordination number of each atom, that is number of nearest neighbors surrounding each atom, is 12. Now out of these 12 neighbors, 6 of them lie in one plane, 3 in an adjacent parallel plane above it, and 3 in a similar plane below it, like this. 6 of them lie in one plane, 3 in an adjacent parallel plane above it, and 3 in an adjacent parallel plane below it. So altogether it is 12. As I said before, closed pack structures are classified into two, which are the HCP, hexagonal closed pack structures, and face centered cubic structure. Then we will, so that this paragraph is important, so you have to study it. Then let us study in detail about the first classification that comes under closed pack structure. What is it? HCP, or hexagonal closed packed structure. Now see how it is constructed. Here, a layer of similar atoms. Consider a layer of similar atom, how with each atom surrounded by 6 atoms in one plane, as shown in the figure given below. Now a similar layer, that is B, is placed in the alternate valleys formed by A layer atoms. Alternate valleys means, suppose that these are A layer atoms. Now in between these A layer, and that is in here, these are called alternate valleys, that is space between these A layer atoms. So in between these valleys you will keep B layer atoms. Okay, that is the arrangement here. So A layer atoms is the first layer, and above A layer atoms, or in the alternate valleys of A layer atoms, we place B layer atoms, that is the second layer. Now what about the third layer it is placed on the top of B layer. How? In such a way that the atoms of new layer, that is the third layer, exactly overlap with the first layer, that is A layer atoms. Okay, so A layer atoms is kept first, that is the first layer, and in the alternate values of A layer atoms you kept the second layer, what is it, B layer, and on the top you keep the third layer in such a way that it exactly overlap with the first layer, that is A layer atoms. So this stacking sequence is repeated and the configuration that you get is AB, AB, AB. So that is the general structure for an HCP crystal structure. Now, so this type of stacking is called HCP, and the structure is called hexagonal closed pack structure. And as the name suggests, what will be the shape of the unit cell? It will be hexagonal. So from this figure you can see that 12 atoms are located at the corners, 2 at the center of the basal plane and 3 completely inside the hexagon. So it is not necessary that you need to draw this figure. It is enough you mention the whole paragraph. Okay, but if possible I think you can draw this figure just to show the stacking sequence. Okay, now another number is effective number of atoms in unit cell. It is 6. So here it is 12 by 6 because there are 12 atoms located at the corners. I already told. Here it is written that then 2 are located at the center of the basal plane and 1 lying completely inside the hexagon. So you will get the effective number of atoms of the unit cell as 6. So if you don't remember this, it is enough you write that the effective number of atoms in unit cell is 6. That is enough. Then the interatomic distance for atoms within the layer is given as A. Then the distance between two adjacent layers is C by 2, where C is the height of the unit cell. So for an ideal HCP structure, C by A, that is the ratio of height to the interatomic distance, is 1.633. All these numbers you have to study because all these are features of hexagonal closed pack structure. So regarding hexagonal closed pack structure, what all things you have to write? How it is arranged, this particular figure, then this paragraph, no need of drawing this figure, then effective number of atoms in unit cell of HCP structure is 6, then this one. Okay, then here they have once again discussed in detail about the structure of HCP. Here they have mentioned that the space lattice is hexagonal, that we know, with bases consisting of 2 atoms in such a way that one atom lie at the origin and the other atom lie at the point or the lattice point 2 by 3, 1 by 3, 1 by 2. That you have to study that. So you can say the space lattice is hexagonal and the bases consist of 2 atoms. One atom lie at the origin and the other atom is located at the lattice point. Remember that point, 2 by 3, 1 by 3, 1 by 2. Okay, now the shape of unit cell, we told it is hexagonal, and the volume of that primitive cell is exactly 1/3 of the volume of the hexagonal cell. Okay, now here the packing fraction is defined as ratio of volume occupied by the atoms in unit cell to the total volume of unit cell. This definition is very important. Okay, packing fraction is defined as ratio of volume occupied by atoms in unit cell to the total volume of unit cell. And here the volume is of the unit cell, hexagonal unit cell, is pi a cube. Here the value of packing fraction is 0.74. Okay, then some examples are magnesium, zinc, cadmium. Then the relation between interatomic distance A and atomic radius R in the case of HCP structure is 2R equal to A or A equal to 2R. So with what all points you got? Effective number of atoms in unit cell is 6, volume is pi a cube, then packing fraction is 0.74, then the ratio of height to interatomic distance C by A is 1.633, then examples are magnesium, zinc, cadmium, then the relation between the interatomic distance A and atomic radius R is equal to 2R equal to A. So these points are all you have to write regarding HCP structure, and then you have to draw the figure and explain the structure. That is enough for HCP structure. Now here, see the packing fraction, what I told, it is written 0.74. Okay, then here they have derived how that packing fraction 0.74 is obtained. Derivation is like this. Total volume of hexagonal unit cell, volume, you know, it is base area into height. Okay, that is again equal to 6 into 6 means it is hexagonal, into area of triangle AOB. Here they have taken the triangle AOB in this figure, into height. Height we know it is C. So 6 into area of triangle is half length into breadth. So half into length, that is BO, into breadth AY. Okay, everything is drawn in this figure, into C. So 6 into half, BO is marked as A in this figure, AY will be as per the figure A cos 30. Then into C, we know it is already given here, root 8 by 3. See, so that is root 8 by 3 A, because C by A is root A by 3. So C is equal to root 8 by 3 A. Now again we are simplifying. 6 into half into what is cos 30, root 3 by 2, right? So this one will get cancelled. This is 3, that is written here. Then cos 30, root 3 by 2, root 8 by 3 is written here. Then A cube, here there is a, here there is a, here there is a, so A cube. So you will get this value on simplification. So packing fraction, I already defined that it is a ratio of volume occupied by the atoms in the unit cell to the total volume of unit cell. So pi A cube, it is already here, pi A cube, volume occupied by atoms in unit cell is pi A cube. Okay, then this is a root, this one is the volume of the unit cell. Okay, so ratio of volume occupied by atoms in unit cell, pi A cube divided by volume of unit cell, which is 3 root 2 A cube. So on simplification you will get the value of packing fraction as 0.74. Okay, next we will see FCC. Here the arrangement of the first two layers can be similar. Now there is a difference in the arrangement of third layer when compared with HCP structure. What is it? Here in HCP layer we told that the third layer exactly overlap with the first layer, that is A layer atoms, but here it doesn't happen. Instead the third layer occupy those positions of A layer which are not occupied by B layer atoms. That is the difference. Here the third layer does not overlap with the first layer, that is A layer. Instead it will occupy those valleys of A layer which are not occupied by B layer. Here the third layer is designated as C. Now the fourth layer will exactly overlap with the first layer. In HCP structure it was the third layer that was exactly overlapping with first layer, but in this case the third layer does not overlap with first layer. Instead it will occupy the valleys of first layer, that is A layer, which are not occupied by the second layer, that is B layer atoms. Instead the fourth layer exactly overlap with the first layer, and this type of stacking sequence is repeated, and for FCC you will get the arrangement as ABC, 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 like that. Now here also a unit cell has a shape of FCC, face-centered cubic. Here effective number of atoms per unit cell is 4. In HCP it was 6. Okay, this is the figure. Here the atoms touch one another along the face diagonal because it is face-centered cubic. Now here they have let A be the length of the cubage and let R be the atomic radius, and from figure they have marked it as, this is A, length of the cubage is A, this is 4R, in atomic distance is marked as 4R. Okay, then here this is hypotenuse square, so 4R square will be A square plus A square. Okay, then So 16 r square will be 2a square. So from that 4 are equal to root 2a. So here the relation between interatomic distance a and atomic radius r is 4 r equal to root 2a. What about HCP structure? It was 2 r equal to a, or a is equal to 2 r. Here it is 4 r equal to root 2a. So you can draw this figure and this expression. Here also the packing fraction is 0.74, that is volume occupied by atoms in unit cell to total volume of unit cell. Here coordination number is 12, packing fraction is 0.74, effective number of atoms per unit cell is 4. The shape of unit cell is face-centered cubic. Examples are copper, silver, gold, aluminium. So closed pack structure is over, and it was classified into HCP and FCC. Now we will learn about loose pack structure. It is broadly classified into two, which are the FCC, face-centered cubic, and simple cubic, SC. Here coordination number is less than 12 and packing fraction is less than 0.74. So let us begin with BCC, body centered cubic. Here, as the name suggests, the shape of unit cell is body centered cubic. Atoms are located at the corner as well as at the body center. So you can draw this figure. Here, effective number of atoms per unit cell is 2. Coordination number, I told it is less than 12. So here, coordination number of BCC is 8. Then atoms touch one another along the body diagonal. Why? Because it is body centered cubic. Now you can draw this figure and write this explanation. Here they are trying to derive, as usual, the relation between interatomic distance a and atomic radius r. So here AC square is equal to a square plus a square, which is 2a square. Okay, this one, AC square, hypotenuse. So this is a and this is a. So AC square will be a square plus a square, which is 2a square. Now what about FC square? FC square, it will be AC square plus AF square. So that will be 2a square plus a square, because AC square is already 2a square. So FC square will be 2a square plus a square, which is 3a square. But what about FC square? FC is actually 4r. It is marked in the figure. So 4r square equal to 3a square. So 16r square equal to 3a square, or 4r equal to root 3a. So what all things you have to write for BCC? Here the shape is of unit cell is body centered cubic, and then the atoms are located at the corners as well as at the body center. Then atoms touch each other along the body diagonal. Coordination number is 8. Then packing fraction is here coordination effective number of atoms per unit cell is 2. Coordination number of each atom is 8. Then the relation between interatomic distance and atomic radius is 4 r equal to root 3a, and packing fraction is 0.68. See, it is less than 0.74, right? Volume occupied by atoms in unit cell to total volume of unit cell. The packing fraction, it is 0.68. If you don't remember all these numerical calculations, it is enough you write packing fraction is 0.68. Examples are sodium, potassium, molybdenum, tungsten. Now the last one, simple cubic structure. Similar explanation. The conventional unit cell has a shape of a simple cube. Atoms are located oddly at the corners, and the atoms touch each other along the body diagonal. Then the relation between interatomic distance and atomic radius is 2r is equal to a. Then packing fraction is 0.52 in this case. Then example is polonium. Okay, so this is a very important session. So you have to this is the most asked essay question. So simple crystal structures are broadly classified into close packed structures and loose packed structures. Close packed structures are again classified into HCP, hexagonal close packed structure, and FCC, face centered cubic structures, whereas loose packed structures are again classified into two. They are body centered cubic, BCC, and simple cubic. And under that you have to draw the figure and explain the construction or how the structure will look like in case of HCP and FCC. And then you have to write the example, then effective number of atoms per unit cell, the packing fraction, relation between interatomic distance and atomic radius, then coordination number, examples, etc. So all these points that is discussed in today's class is important. So this is a very sure question which is asked as an essay question. Okay, so please study well this part. Okay, thank you.